Hello, welcome to part one of 2 lectures on metamorphic rocks. In these lecture series, we're going to be thinking about how metamorphic rocks form. So these are rocks that have undergone high pressures and temperatures such that the mineral compositions alter into new minerals, or they rearrange their orientation. However, we do not get full melt. As we go along, we're going to be thinking about the differences in these two rocks here. So both of these rocks displayed are metamorphic rocks. This black one and this green one here. So we have some slight differences in color between these rocks, as well as some slight differences in their textures. And throughout this lecture, we'll think about both that textural comparison and the compositional comparison. All right, so let's start out with what metamorphism is and the different ways in which metamorphism can occur. Metamorphism is described as the transformation of rock in a solid state. This means that there is very little to no amount of melt. If the rock melted, it would form a magmatic mush or magmatic body that would then cool into an igneous rock. So we have to very carefully toe that line of increasing pressures, temperatures, and chemical conditions such that the rocks remain solid but change either their mineral types that are displayed or change the orientations of minerals. Some examples of metamorphic conditions include hydrothermal fluids that can alter the chemical conditions. So last week we talked about hydrothermal vents or black smokers at divergent boundaries, these locations where magmatic igneous bodies are heating up seawater, and that seawater is kind of extruding out in these hydrothermal vents. Those contain slightly different chemical conditions and can result in nearby alteration of the rock. We can also get rocks being buried in subduction zones. So this area called the accretionary wedge, which is kind of the scraped off sediments of the oceanic crust. If this continues down, that subducting plate is going to be subject to higher pressures and temperatures that can lead to metamorphism. So that can happen through that burial as well as the pressures of plate convergence, which exerts that pressure difference and can again cause metamorphism. So as rocks are undergoing increasing pressure and temperature, they go through a few different stages of which metamorphism is only one. So initially, as rocks are subject to pressure and temperature increases, they actually undergo diagenesis, which is not quite metamorphism yet. As pressure and temperature conditions increase, that'll alter into metamorphism, which under even higher pressure and temperatures becomes melt, which would get us back to an igneous rock. So completing part of that rock cycle chain. In diagenesis, this first stage of pressure and temperature increase, this tends to occur to sedimentary rocks more so than other rock types. And this is just an alteration to those sedimentary rocks from that increase in pressure, from increased water infiltration through the sedimentary rock or movement through pore spaces, and through later microbial activity. In diagenesis, the sedimentary rock stays a sedimentary rock. So we're not undergoing any alterations to the chemical form that's extreme enough to make it metamorphism. Instead, what we often see is alteration to contain more clay minerals. So we've often talked about clays forming through chemical weathering, and now we see another example where clays can form through diagenesis. So what I want you to remember as we're going into metamorphic rocks is that clays can be very common, especially in these increasing pressure and temperature conditions. And just as an example of what a clay looks like, this is a common clay called kaolinite. It smells like earth. So if you have a hand sample of kaolinite, one way to identify it is that it's fairly soft and it smells earthy. As those rocks are then subject to increasing pressures and temperatures, the grains will start to actually alter. So for example, we'll get new minerals forming, such as micas. This is especially common when we start out with a clay that goes through increasing pressure and temperature to metamorphose, and that clay will contain the right elements to form micas, and now will be under the correct pressure and temperature conditions to actually grow those mica minerals. This onset is fairly fuzzy, but it tends to occur when we get to about 10 kilometers depth and 200 to 400 degrees Celsius. So anything less than this is probably in the realm of diagenesis. As we continue to increase in depth and increase in temperature, we eventually cross into the melt zone, which is when rocks cross the solid-liquid boundary. And so here they're going to actually start to melt and form part of that igneous rock cycle. So we can see an example of this cycle on the right. We've got that clay mineral that formed through diagenesis being altered into a biotite, which is a mica mineral. These micas are characterized by their platy look. So they look like sheets of paper, although they're transparent, and they're often bound together, just like sheets of paper are in a booklet. So you can see the edges of all these leaves on this side here. And then as this biotite goes through even more pressures and temperatures, it eventually becomes a melt. So the general principle of metamorphism is that rocks are going to form in one set of pressure and temperature and chemical conditions. This is the condition under which they are stable. If you change those conditions, they are no longer stable. And so the minerals that make up those rocks are going to start to react to form new mineral assemblages that are stable. Under increasing pressure and temperature conditions, we're going to see the overall chemical composition stays the same, but those chemicals will be arranged in different minerals. We call these original rocks here the protolith. So that's the parent rock, if you remember Greek roots. And an example of this is a shale rock. So remember, this is made of clays. And if we increase the pressure and temperature in this shale, we eventually get to a metamorphic rock called a gneiss. And it's pronounced like the word nice, even though it looks like it might be gneiss. This means once we have the final resulting metamorphic rock, we can backtrack through looking at the chemical composition, the minerals that are there, and the textures. We can backtrack what these new pressure and temperature and chemical conditions were, as well as what the protolith was. So this blue arrow that I show here going from shale to a gneiss, we can start to use that gneiss to infer back to get to that shale. So this is kind of the main storytelling that we'll do with metamorphic rocks, are using them to figure out what pressures and temperatures they were formed at and what the original rocks were. And this tells us how the Earth has been subject to different pressures, which relates back to tectonics. So from this, we can infer how plates have been moving around the Earth in the last billions of years and back out assemblages like supercontinents. Through the protolith, we can also look at what conditions were like. Were we in marine environments? Were we mostly on land? Those sorts of things. So how does this metamorphism actually occur? At the very beginning, we briefly went over a few different mechanisms for metamorphism. However, they can be grouped more broadly into three types: contact, dynamic, and regional. So this contact metamorphism is going to involve high temperatures but low pressures. Dynamic will be high temperatures but low pressures. And then regional will be high pressures and temperatures. So regional has both of them being fairly high. So we'll start out with contact metamorphism. Contact metamorphism is driven by temperature increases only. As that summary slide showed, it's a high temperature but low pressure type of metamorphism. And this really means that we have to have rocks that are proximal to some high temperature body, which usually occurs when we have things like a magmatic intrusion. So the rocks that surround the magma chamber, as well as the rocks that surround any dikes or sills that come up from that magma chamber. These are all going to be subject to contact metamorphism. This is going to work through increasing temperatures, which will act along a gradient. You have something hot, it's going to want to diffuse out around it to spread that heat out. And so that heat is going to travel through the surrounding rocks and alter their conditions and alter their mineral assemblages. We also see cycling of water that is maybe released or associated with this magma chamber, and heated water systems that can increase the rates of ion movement, and that tends to accelerate chemical reactions and allow the metamorphism to occur in a little bit more of a rapid manner than it normally would have. We call this area around the hot body that has undergone contact metamorphism, we call this the contact aureole because it forms in somewhat of a halo shape around those hot magmatic bodies. And that's shown in blue in this diagram here. The size of this contact aureole or halo is going to be really dependent on the temperature conditions and the water content. So you can see in this diagram that the size of this blue contact aureole is different depending where you are within the subsurface. And in particular, it seems to be a lot wider in this white layer here, which is a limestone, right? And that's going to be due to how that heat in the water is transferred in limestone compared to the shales and sandstones, where that transfer is going to be more limited. And so there is a smaller zone of contact metamorphism. The size will also vary depending on the size of that intrusive body. So for example, really large batholiths, so really large intrusions of granitic magma, for example, the Sierra Nevadas or Pikes Peak, tend to create contact aureoles that are about 1/2 to 1 mile in size. Whereas things like dikes, which tend to be meters in scale, will form contact metamorphism aureoles on the scale of several feet. Because this type of metamorphism doesn't involve any pressure, there is no lineation that forms. There's just going to be a change in the chemical makeup and the mineral assemblages. So this results in a type of metamorphic assemblage called a hornfels. And these are rocks that have been metamorphosed, so they're metamorphic rocks, but there is no mineral alignment. A mineral alignment is going to be caused by pressure differentials. So if you pressurize a system by kind of pushing two things together, you can imagine that those things in the center will start to align based on the pressure directions. Since contact metamorphism doesn't contain any pressure, we don't see that alignment. So here are some examples of what these look like. This is a hornfels on the lower left here, and you can see that it kind of has this massive look. There's no texture to it that might indicate alignment of minerals. Another example of a hornfels is shown in the center here. Even though this looks like there is some alignment, it turns out this is the original layered sedimentary rock. So these are actually layers of shales that form the dark and the light banding here. And we can tell that this is a hornfels and not actual mineral alignment if we look more closely at the minerals themselves. So if we were to take a thin slice of this, put it on a microscope slide, and look at it under the microscope view, we would see something similar to the upper right here. The view across is about 2 millimeters. And we can see here's all the black and gray. These all represent individual minerals, and these minerals are not aligned with each other. We'll see some examples in a little bit of what mineral alignment looks like. And it is very directional. It's pretty clear when the minerals are aligned. So because contact metamorphism depends on heat, and the heat is coming from one source, we often see a gradation outward from that source of degree of contact metamorphism. So closest to the igneous body where there's the most heat, we're going to see the highest grades of contact metamorphism. As we go out towards the surrounding cool rock, we'll start to see lower and lower amounts of metamorphism until eventually we get to the protolith or the original unaltered rock. This series of contact metamorphism sort of facies that we see are going to be dependent on what the original rock type is and what the temperature is. So we can see some examples of this here. When we look at a sandstone tends to just form a quartzite when it has been under metamorphic conditions. This is because a pure sandstone is made of just quartz, and so there's no minerals that it can change into. Quartz is the only mineral that could ever exist. However, as we get into shales, we start to see more of a gradation. And so this is reflecting how clays change as they are subject to higher temperatures. So under lower temperatures, we tend to get some metamorphic rocks that contain muscovite and chlorite minerals. Under higher temperatures, that'll change to biotite and andalusite. Even higher temperatures, we'll get cordierite and sillimanite minerals. And then last, we'll get hornfels. In limestones, because the kind of main mineral in limestone is a calcium carbonate, it's going to behave similar to that sandstone, where there's not really any further alteration that can occur. The calcium carbonate will stay calcium carbonate, but the interlocking mechanisms between the calcium carbonate minerals may change. So we go from a calcium carbonate marble that is fairly fine grained to one that is coarser grained at higher temperatures. Right, so these are just some examples of how the original composition of the rock and the temperatures result in slightly different metamorphic rocks and contact metamorphic conditions. We'll see some other assemblages when we look at regional metamorphism. All right, so the next metamorphic type is dynamic metamorphism. This one is also going to contain high temperatures and low pressures, or high pressures and low temperatures, sorry. We are backwards there. So let's fix that. So this occurs through extremely rapid events. So things that will very quickly increase pressures, but will increase pressures for such a small amount of time that temperature does not have any time to respond. So this occurs through things like bolide impacts, which you can see in the upper right here, or earthquakes, where we have a lot of pressure between the plates, they suddenly slip, but that occurs at such a rapid scale that there is no time for any temperature diffusion. In dynamic metamorphism, because of the high pressures, we tend to get a lot of fractured, ground, and recrystallized rocks. There's often some heat generated by friction, but I really want to emphasize that these are kind of messy metamorphic conditions. So the rocks that we get from dynamic metamorphism tend to be pretty messy looking themselves. We get things like breccias, which are rocks that have been fractured and ground. These are actually not a metamorphic rock. They don't undergo quite enough pressures to become metamorphic. They're actually sedimentary. And they would look a lot like a conglomerate, but be composed of material that is very angular instead of smooth material. However, as we get a little bit higher pressures in dynamic metamorphism, we start to get into true metamorphic rocks like mylonites and pseudotachelites. So mylonites are highly fractured and ground rock. It often contains a little bit of secondary mineralization. And they're found quite frequently near faults as well as near old impact craters. If we get to even higher pressures during dynamic metamorphism, we form something called a pseudotachelite, which is so fractured and ground and pressurized that it actually forms a glass-like form. So these almost look like layers of glass within the Earth's subsurface, and they record these fossil earthquakes, times when we had really high pressures over a very small zone. So here some pictures of these. This is a breccia, so you can see how this compares to a conglomerate but has more angular pieces within it. And these pieces can vary quite a lot in size, from being on the scale of meters to being on the scale of centimeters or decimeters. These myelinites that are fractured and ground may look something like this rock here. So because there is some pressure, quite a lot of pressure to them, they have a very directional look to them. So you can see how everything is kind of elongated in the same directions. And if we were to take a slice of this and look at it under a microscope, we would see some evidence of that secondary mineralization. So this is an example of a myelinite from the Himalayas. We're looking 7 millimeters across in the view here. And you can see the original larger grains. These are from the original rock before the dynamic metamorphism event. That increase in pressure during dynamic metamorphism caused a lot of shearing and fracturing of the surrounding rocks. And those sheared grains are going to represent some secondary mineralization process. Right, if we increase that even more, we get these high pressure pseudotachelites. So this is an example of a peridotite in Italy that has a pseudotachelite vein in it. It's this big, or not big, but very stark, glassy and dark vein that I'm outlining here. This is a record of an old earthquake. So at one point in the past, when this rock was still buried below the surface, there was a rupture along this plane here. And that plane was the earthquake plane, where the rocks slipped against each other under high pressure. They fractured, and then they quenched and formed a glassy vein called the pseudotachelite. And when you look at this in that microscope thin section view, again, this one is also 7 millimeters across. All this black area is that glass that you see where everything is so fractured and ground up that the backlit light isn't able to penetrate through it. We also see some spectacular pseudotachelites that form as a result of bolide impacts. So this is an example from South Africa, from the Redeford impact crater. And what you see here are these sort of brecciated, larger clasts. And then surrounding those is that pseudotachelite. And that is from that really high pressure event. Okay, so the last form of metamorphism is one that we may see a little bit more often, and it's associated with convergent boundaries where we can get high pressures and high temperatures. So the pressures are occurring over a long enough period of time that the temperature is also going to increase. There are two subtypes to regional metamorphism, and this depends on the direction of pressure. So a lithostatic type of regional metamorphism occurs in this area in the orange box here. And in this area, the rock is buried by other rock. That buried, the kind of overriding rock exerts pressure on the buried rock. This is called lithostatic pressure. It's just the burial pressure. And that pressure is pretty equal in all directions. And so because it's equal pressure, we tend to get metamorphism that doesn't have any sort of what's called foliation to it. So there's no directional alignment of the resulting metamorphic rock. In contrast to that, directed or dynamic regional metamorphism has gradients of pressure to it. So this is going to be really associated with tectonic forces, as shown in the blue box here, where you have two tectonic plates, for example, colliding and converging with each other and forming really strongly directional pressures. There's still some overburden pressure, lithostatic pressure, but that pressure is sort of outweighed by this dynamic and directed pressure. So the resulting rocks are really going to record that directed pressure in the form of foliation. And one way I like to think of foliation, which is somewhat similar to what goes on here, is if you take a piece of paper and you start to press on it laterally, it eventually folds, and the direction of the new sheets of it is perpendicular to the force that you were exerting on it. And in that same manner, minerals, especially micas, which are those very flat paper-like minerals, are going to form foliation that lies perpendicular to the direction of the stresses. So we can see that occur as we look at the metamorphic textures. So we'll go through metamorphic textures starting from non-foliated to highly foliated. Most of the metamorphic rocks that we see are formed during this directed regional metamorphism. So the degree of foliation is going to be fairly important in determining how to name metamorphic rocks and how to interpret metamorphic rocks. So when we start out, we have non-foliated rocks. In these rocks, the minerals are not aligned. So this either means there's been no metamorphism yet, or the metamorphism has been non-directional, such as contact. The other exception here is that all of the minerals are quartz. And this is because quartz forms what's called an equant or euhedral grain that can't align itself. So no matter what pressures you exert on this, the quartz grains are still going to look like a jumbled assemblage of quartz grains because there is no slightly thinner side for that quartz to align to. So it will always be non-foliated. So for example, if we're looking at a subduction zone, these non-foliated minerals would tend to be found closer to the surface, like in that accretionary trench, where we have some sediments coming together, but they haven't yet experienced a lot of burial or a lot of temperature increases. As we start to increase and bury that sediment with increasing depth, so increasing pressure and temperature, we start to get the earliest signs of foliation. And this is called a slate foliation. In this foliation, we have planar minerals that are aligning. So this is often going to be clays. Clays look a lot like micas in the sense they have a very flat side to them. They look like a sheet of paper. And so as they undergo slate foliation, those clays, which may have been randomly oriented, now start to orient in the same direction that'll be perpendicular to the main forces. However, clays are fairly small, and so slate foliation has this alignment, but the alignment is small enough that we can't see it unless we are looking through a microscope, right? So this is a 40 times zoomed look at the rock. As we increase the pressures and temperatures, we start to get more chemical rearrangement within the rock, and we get into schist foliation, where the planar minerals are aligned, but those planar minerals are now going to be clays and micas, right? So the micas are developing. These would be things like a biotite, or a muscovite. And these are large enough that you can see them with your naked eye. So if you'll note in this image here, we're now at 1 time zoom, which means we're just looking at it with no magnification. So at schisty foliation, the rocks have subducted or been subject to more pressures and temperatures such that micas are developing, and we can actually see the foliation with our naked eye. At even increased pressures and temperatures, those micas, in addition to being aligned with the pressure directions or perpendicular to the pressure directions, will now start to group themselves. And this gives us gneiss foliation, again, pronounced like the word nice. And here we have planar mica minerals that are aligned. We're not going to have that many clays. So X on the clays. They're aligned, they're visible with the naked eye, but all the minerals are also starting to make distinct bands. And so between these bands where we have the dark planar mica minerals, we may have secondary growth of other types of minerals like quartz that have developed between the schist and the gneiss foliation. So how do we name these rocks? Well, we name them by that texture and by that foliation. So metamorphic rocks tend to primarily be named by the texture. There are some exceptions, but especially when we have regional metamorphism that is directed, they're named by the texture. So we'll start out with the lowest of these, which was the slaty textures. And these rocks are just called slate. They are always from a shale protolith. So anytime you encounter a shale or anytime you encounter a slate, you know that it formed from a shale and that the original environment on the Earth must have been a very low energy environment with a lot of muds and clays in order to form a shale. The slates are a fairly low metamorphic grade. And so the grade is another name for the pressure and temperature conditions. A low grade is low pressure temperatures and a high grade is high pressure temperatures. Because it's undergone a fairly low amount of metamorphism, it looks fairly similar to the protolith. So a slate and a shale are pretty hard to differentiate. Visually, they look somewhat similar, although the slate is going to have some layering to it. So you can see in this picture on the right, there is this kind of layering that is parallel and represents the foliation. This layering can actually cut across the original sedimentary bedding. So if you go, there's these stone benches that are north of Palmer Hall, and they actually contain what is drawn in this image here, where there is an original bedding plane, as shown in kind of these dashed lines here, and then regional metamorphism occurred at an angle to that bedding plane and aligned the clay minerals along a new foliation, which is shown in the black lines here. So when you look at the resulting rock, you actually see two planes to it. You can see that original bedding going this way, and then you can also see the foliation cutting across it. So if you have time and you're on campus, check out those stone benches just north of Palmer. They're gray, and you should see the sign of the bedding and the foliation overlying it. The other way to tell slates and shales apart are that slates tend to make a ping sound when you drop them or when you hit them. And this is simply because they are a little bit more indurated and more set together than the shale is. All right, if we increase the metamorphic grade, we get a rock that we didn't actually go over earlier. It's called a phyllite, and it is somewhere in between the slaty texture and the schisty texture. So a phyllite tends to come from a shale or a siltstone originally, and is at a medium metamorphic grade. The difference between a slate and a shale, or a slate and a phyllite, is that the phyllite has started to develop crinkles in the foliation, and it has started to grow micas. So remember, micas are those platy minerals, and they often tend to be somewhat shiny. These micas can be seen with a hand lens. So they're not quite at the level where you can make them out with your naked eye, but they're visible at about 10 times zoom. Because these micas are there, the phyllites kind of have this shiny look to them that's not present in slates, which you can see in these two examples here. And that's light reflecting off of those shiny micas. Next up are schists. These are again going to form from a shale or a siltstone, but now we're at a medium to high grade. So you can imagine this shale or siltstone that we started with originally became a slate, which then underwent higher pressures and temperatures to become the phyllite, and now has undergone higher grade conditions to become a schist. At the level of a schist, the micas have now grown to be visible by the naked eye. So in both of these images, you can see that reflective nature of the micas, and you can make out the individual micas within both of these rocks. The micas have oriented to be parallel to each other and perpendicular to the direction of main stresses. And schists have increased the pressure and temperature conditions enough that what are called porphyroblasts may grow. And these are large crystals that form during metamorphism. So they form during increasing pressure and temperature conditions. And a really common one are garnets. So this is an example on the right of a garnet in a chlorite schist. This means it is a rock that is schist texture, contains mostly the chlorite mica, and then also contains some garnets. These garnets tend to be equant, so they are equal in all dimensions. which is why you don't really see them forming the foliations that the micas form. All right, and then as we've increased that metamorphic grade even more, we get to the gneiss. So these are again that shale and siltstone protolith, but now the increased pressures and temperatures have caused banding. So rather than just mineral alignment, we're now getting mineral segregation with usually dark minerals grouping together and light minerals grouping together. For rocks that are formed from shales and siltstones, these are often alternating layers of biotite and quartz. These also contain porphyroblasts, so you can see some very small red dots in here, and these are likely very small garnets that formed. Okay, so the slate, phyllite, schist, and gneiss rocks are all names for foliated metamorphic rocks. And I'd like you to fill out this table to recognize for each of these, what is the foliation, what is the layering, and what are other diagnostic characteristics about each of these rocks. So pause here and fill out this table, and when you are ready, go to the next slide. Okay, next slide. So this is how I filled it in. The slate, you can see some foliation, but it's mostly micas and clays and that are too fine to see. Whereas the phyllites, we have micas aligning and giving it a satiny luster, and those micas are visible in a hand lens. Under a schist foliation, we still have micas aligning to create that schistosity, but the micas are now visible by naked eye and may be surrounding porphyroblasts. Finally, at the gneiss stage, we have compositional banding rather than just micas aligning. So we have micas that are again visible by the naked eye and often separated by layers of black and white banding. And we can also have porphyroblasts. All right, so that is the end of part one, where we've really gone over the different ways that metamorphic rocks can form and the different textures within them. So we'll go back to this question of what is the difference in the histories of these two rocks? And I would like you to now try and apply those textural clues to guess what texture each of these are. And I'll let you know each of these are formed under dynamic regional metamorphism. So those textures we just went through do apply.